Okay, so in addition to graphical summaries, you also can use numerical summaries. So we can either use univariate statistic, bivariate statistic, and autocorrelation. So univariate statistic for the single series, this we call univariate. Univariate means that only one variable. So it is single series. Bivariate statistic we use to represent statistic or represent relationship between two variables. So bivariate means two series. So autocorrelation, relationship between current and past. Okay, later on I will explain more on this. Okay, so in addition to graphic, it is also useful to provide numerical summaries. That is, summary number for a data set is called statistic. So remember that you have two types of different terms, the statistic and parameter. So parameter represent what we call the true value for the population. But normally when you have a sample, then you I mean the summary, the numerical summary, that one we call as statistic. So for a single data set or time series, common distributive statistics are the mean, standard deviation, and variance. So you have one single series, then you can use this statistic to represent what we call that the summary of the series, the mean, the average, mean average, standard deviation, and variance. For a pair of data set that is bivariate data, it is of interest to describe how the data set relates to each other. Common summary statistics are covariance and correlation. So for a single time series, it is very useful to compare the observation at one time period with observation at another time period. And most common statistics are autocovariance and autocorrelation. So you can see quite similar terms, covariance and autocovariance, and then we have correlation and autocorrelation. So what's the difference between the two? So it's slightly different. So here we add auto. So later on I'll explain. Okay, now. So this one, if you have X and Y, you have two variables, X and Y, then you can use covariance and correlation to represent the relationship between the two variables. But you only have one series, but we use the same concept of covariance and correlation, but we put, to represent relationship between current and past values of the same series. So we call this autocovariance and autocorrelation. So for the univariate statistic, let's say you have a single series, y, the variable y, y1, y2, and so on up to yn. So you can use the summary. So the mean by taking average of the all values. So this is the mean of the series. And then median, middle observation if n is an odd number. So average of middle two observation is if it is an even number. So if odd number, just the middle one. And then if the number of observation is even numbers, let's say 10, then you take the average of the middle two observation and get the median. And then mean absolute deviation. Okay, the absolute difference between between the value, each other value and the average. So you take, and then you take sum of them, you take average, you divide by sample size, and then you get the mean absolute deviation. Mean square deviation, the difference between each of the value and the average, and then you square the value, and then you take sum of them, divide by sample size, you get MSD, mean square deviation. And the variance and standard deviation given by this formula. Okay. So whenever we are dealing with paired observation or bivariate, it is of interest to examine and measure the extent of the relationship between the two variables. Suppose the two variables are X and Y. A statistic which measures how the variables covary called the covariance is defined as this formula. Okay, so if you have two different variables X and Y, and then you can use covariance to represent how the two variables covary. Covariance means how they are moving together, whether they are moving to the same direction or they are moving to the different direction. Okay, so normally if you have positive, the covariance between X and Y is positive, meaning that when X increase, Y will increase as well in the value. But if the covariance is negative, when X increase, Y decrease the value. So However, the covariance does not tell us how strong the relationship between X and Y. It just tells us how the two variables covary. Okay, whether they are moving to the same direction or they are moving to different direction. Depends on the value of the covariance, whether it is positive or negative. So the covariance takes on the uniques of this variable under consideration. Okay, so it depends on the covariance, depends on the units of measurements. Okay, it's possible that the covariance can be small values, or it also can be large value, 1,000 or even a million. Okay, it's also possible. But the values, whether it's small or large value, it does not tell us the strength of relationship. The strength of relationship between two variables, whether there is strong relationship between Y and X, or there is a weak relationship. So in order to know the strength of relationship, then you need to use what we call as correlation. So a unitless measure describing, so meaning that it does not depend on unit, it does not have a unit. So a unitless measure describing the relationship between two variables is the correlation coefficient, which is given by this formula. So the effect of scaling is to restrict the range of correlation to the intervals -1 to 1. So we know that correlation can only take values in between -1 to +1. So cannot be more than 1, cannot be lower, cannot be smaller than -1. So in this case, if let's say the correlation between X and Y is close to -1, we know that there is strong but negative relationship. When X increase, Y decrease. If the value is close to +1, then we know there is positive relationship. When X increase, Y increase as well. But is the value of correlation just around 0 or close to 0 or even 0, then there is no or weak relationship between X and Y. So again, so covariance just tells us how the two variables covary, whether they are moving to the same direction or they are moving to different direction. But if you divide covariance and the standard deviation of the two series X and Y, so covariance of X and Y divided by standard deviation of X and Y, standard deviation X, then standard deviation Y, then you get what we call as a correlation. And correlation tells us how strong the relationship between the two variables X and Y. So for example, the covariance, if let's say between two variables P and M is -71, so we know that the two variables are moving to the different direction. So when P increase, M decrease. So indicating there is a negative relationship between the two variables. And then if the correlation coefficient Rxy equal to -0.73, because it is negative, then and because it's correlation, then we know that the minimum, the smallest value is -1. So indicating that there is a fairly strong negative relationship between the two variables, because -0.73 is quite close to -1. Okay. Okay, now autocorrelation. The covariance and correlation coefficient are statistics that measure the extent of the linear relationship between two variables, and it is used to identify exponential relationship. Autocovariance and autocorrelation are comparable measures that serve the same purpose for a single time series. Okay, so this one, autocovariance, the covariance and correlation we use to represent relationship between two different series, or we call it as bivariate series. Okay, but we also can use the same concept of covariance and correlation for the same series, different observation within the same series. So autocovariance and autocorrelation are comparable measures that serve the same purpose for a single time series. So we have a time series variable, a time series data. So Y1, the first observation, second observation, Y2, and so on. So YT be a time series. So if we compare YT, the observation at time t with YT minus 1, the observation at time t minus 1, then we can see how consecutive observations are related. So if you have monthly data, it's just like you compare current month and previous month, the relationship between current month, previous month. Okay. So observation at YT, the observation YT minus 1 is described as lag by one period. Similarly, it is also possible to compare observation lag by 2 period, 3 period, 3 period, and so on. Okay, so consider this data. Let's say just now, previously I explained to you that if let's say we have bivariate data, two different series Y and X, and then you can use covariance in order to know how the two series, so this have the first observation, second observation, and so on. So how the two series covary, whether they're moving to the same direction or they are moving to a different direction. Okay, and then if you divide by the standard deviation of X, standard deviation of Y, and then you get the correlation. Okay, correlation, we know that correlation take value between -1 to +1. So cannot be smaller than -1, cannot be higher than or greater than +1. So it tells us how the strength of relationship between two variables. But let's say you only have one series, the time series data like this. So it is time series data, let's say monthly data. So you have monthly data for January, February, March, April, and May. You have data, monthly data. Basically, you only have one data, but you can just use the same concept of covariance. Okay, you can compute covariance between current value and the previous value. So this is what we call leg one and leg one. Leg one. Okay, current and leg one of the series. Current value and the leg one, the previous value. So let's say you have monthly data. So if this is January, this is data for February. So meaning that you want to assess, you want to know how the values of the current month and previous month. Let's say this one February and January. So this one March and February. So April and March and so on. Current and previous month. So this is leg one. Current value of Y and leg one of the series. So you also can compute the covariance, because we assess covariance for current and previous value. Then we call it as an auto. We put auto. We add auto term in front of the covariance, so we call it as auto covariance. So similarly, you also can get auto correlation between the two series, current value and the leg one of the series. And then you can do the same for current value and leg two. Okay, leg two. So okay, you get leg one. You don't have the first one because the first one YT the January we don't have data for before January, December we don't have. So so that's not available. So you can only have this one. You can assess relationship between these four observations. Okay, but for leg two, so this current value, you also can assess relationship between current and the what we call the leg two of the series. So in this case, you don't have the first two because we don't have. So this one you don't have the first two. This one also have the what we call leg two of the series. But this one you have. This one leg one. This is the current value. Leg one, leg two. Leg one Y2, leg two is Y1. So you put Y1 here. So similarly, this one Y4, leg one is Y3, leg two is Y2. You put Y2 here, and same for this one. So this current value and leg two of the same series, and then you can do the same. You also can measure the covariance between this and then this current and leg one, and then you also can compute, or you can measure the auto correlation between the two series. This is another example: current value and leg three, current and leg three, so that you can only assess between this and these two series, Y4 and Y1, and Y5 and Y2. Okay, so this is the formula to compute auto covariance at leg K. So at leg K, I mean, if YT and YT minus 1, it is leg 1. If YT and YT minus 2, it is leg 2, and so on. Okay. And then auto correlation at leg K is calculated or given by, I mean, you can compute using this formula. Okay. So this one depends. This one is still the same, YT minus the average. And then this one YT depends. If leg 1, T minus 1. If leg 2, T minus 2, and so on. So together the autocorrelation at leg 1, 2, and so on make up the autocorrelation function, or ACF. A graph of the ACF is called a correlogram and helps one visualize the ACF quickly and easily. So you have now, just now you have autocorrelation at leg 1. You also can compute at leg 2, at leg 3, and so on. And you put the values in a graph, in a diagram, okay, and then it called it as a correlogram. Okay, so we call it as autocorrelation function, or ACF. a graph of the ACF is called a correlogram and helps one visualize the ACF quickly and easily. So this is an example of a correlogram for the given series. This one, the beer production. So a plot of the ACF is a standard tool in exploring a time series before forecasting. It provides a useful check for seasonality, cycle, and other time series pattern. The seasonal pattern is very clear in the ACF or the beer production series. Why? Because you can see that because this monthly data, so you can see the first bar, this one represent autocorrelation or correlation between YT and YT minus 1. The second one between YT and YT minus 2. The third one, YT and YT minus 3. So you look at this one, number 6, it's YT and YT minus 6. Up to this one, number 12, it is YT and YT minus 12. So meaning that the relationship between months of the current year and then the same month last year. So meaning that if you are looking at January this year, so YT and YT minus 12 means the relationship between the January this year and January last year, between February this year and February last year, between March this year and March last year, YT and YT minus 12. So you can see there is strong correlation between the values, between the two values of the same month, this year and last year, So it indicates the presence of seasonal variation, okay, because the values of production this year for January depends on the production value of for January last year. So similarly for production, the value of production for February this year, it depends on the value of production last year. So there is a relationship between what we call the values for this year and last year. So you can see at leg 12, YT and YT minus 12, it has high value. So it indicates for the presence of seasonal variation. So the ACF also helps identify if previous values of the series contain much information about the next value. So previous value, let's say YT and YT minus 1. So meaning that current month and previous month. So leg 1, YT and YT minus 1, leg 1. So, okay, and then you can see between YT, YT minus 2 and so on. So whether there is a little relationship between the one observation and the next. So this tells us whether there is what we call a strong relationship between current value and the past values of the same series. So this one between current and previous month, and this one between, leg 2 YT and YT minus 2 and so on. So the autocorrelation function, the ACF plays a very important role in time series forecasting. So that by looking at the correlogram, it can tell us whether there is seasonal anomaly. It's useful for us to know whether there is seasonality or seasonal variation in the series or not.